September 27th, 1941, Richmond, California. The morning fog still clung to San Francisco Bay when Joseph Welder clocked in for his first day at Kaiser Shipyards, yard number 1. He'd driven west from Wichita with his wife and 2 children, chasing the promise of steady work at $18 a day, more money than he'd seen in 5 years of Depression-era farming. The employment office had been blunt during his interview 3 days earlier. Ever built a ship before? No. Ever welded steel? No. Can you start Monday? Yes. Now Welder stood at the edge of a construction basin stretching 400 yards, watching crews swarm over the skeletal frame of a cargo vessel. Sparks showered from 100 welding torches. Cranes swung massive steel plates through the air. The noise was overwhelming, an industrial symphony of hammering metal, grinding wheels, and shouted instructions barely audible over the chaos. His supervisor, a man named Dutch Hendricks who'd spent 30 years building bridges across the American West, handed him protective goggles and a leather apron. You'll learn to weld vertical seams on bulkhead sections. 2 weeks of training, then you're on the line. We're building these ships in 60 days now. Soon it'll be 40. The Germans are sinking our cargo vessels faster than traditional yards can replace them. Every day counts. Every weld matters. 2 weeks to learn a skill that maritime craftsmen traditionally spent 4 years mastering as apprentices. Welder understood what that meant. The shipyard wasn't training craftsmen. They were training specialists who would repeat one specific task thousands of times until it became automatic. Not artists, but assembly line workers who happened to work with fire and steel instead of bolts and sheet metal. The training began that afternoon in a covered workshop removed from the main construction area. 12 new welders, none with maritime experience, gathered around an instructor named Frank Morrison who'd worked merchant ships before the war. Morrison didn't waste time on theory or history. He demonstrated the basic mechanics of arc welding, striking an arc, maintaining proper distance, controlling the bead, then handed each trainee a torch and a stack of practice plates. Weld these seams, vertical only, same motion every time. I'll correct your mistakes. By Friday, you'll be doing this in your sleep. If you're enjoying this deep dive into the story, then hit the subscribe button and let us know in the comments from where in the world you are watching from today. Morrison's prediction proved accurate. By the end of week 1, Welder could lay vertical beads that passed visual inspection. They weren't beautiful, but they held. Week 2 introduced him to the actual bulkhead sections he'd weld in production. Steel plates 8 feet tall, assembled in the prefabrication shop, waiting for welders to join them into watertight compartments. The process was simple enough. Position the electrode, strike the arc, run the bead from bottom to top, repeat on the next seam. Move down the line as each section was completed. Don't think about the ship as a whole. Focus on the seam directly in front of you. 1 weld at a time, 1 section at a time, 8 hours a day, 6 days a week. October 12th, 1941. Welder's first day on the production line. He was assigned to a team of 8 welders working bulkhead sections for Liberty Ship Hull No. 7. The sections arrived from cutting and forming areas, positioned by crane, tack welded in place by specialized crews, then released to the welders for final joining. The supervisor's instructions were clear. Start at the bottom of each vertical seam, work your way up. When you finish one section, move to the next. We've got 40 sections to complete today. Keep pace with the line. Welder noticed something immediately that troubled him. As each welder finished their assigned seams and the section cooled, the steel plates visibly warped. The distortion was subtle but unmistakable. Plates that had been perfectly aligned when he started welding had developed slight bows and twists by the time he finished. The metal was moving, responding to the intense heat and subsequent cooling in ways that looked wrong. During the lunch break, he mentioned it to Morrison, who'd been reassigned as a roaming quality inspector. "The plates are warping? Is that normal?" Morrison shrugged. "Steel moves when you heat it. That's physics. The engineering department designed these sections to account for it, not your concern. Your job is welding seams, not questioning the process." But Welder couldn't stop noticing it. Over the following weeks, As he welded hundreds of bulkhead sections, the pattern became clearer. The welding sequence they used, starting at the edges and working inward, or beginning at one end and running straight to the other, was fighting against the metal's natural behavior. Each cooling weld contracted, pulling the steel. When welders locked those contractions in place by completing all the edge welds first, the entire section carried that stress permanently. He began experimenting during lunch breaks with scrap plates the yard discarded. He'd weld test sections using different sequences, starting from the center and working outward, alternating between different areas rather than completing one region before moving to another. The results were striking. Center-out sequences produced flatter sections with visibly less warping. November 1941 brought the first rumors of trouble from the Atlantic. Ships were developing cracks, not battle damage, but structural failures in cold water. The yard supervisors mentioned it during morning briefings, emphasizing the need for quality welds and proper inspections. But nobody suggested the welding sequence itself might be creating problems. By December, Welder had welded bulkhead sections for 9 Liberty ships. Hull 7 had launched in late October. Hull 8 followed in November. Hull 9 sat nearly complete on the ways, scheduled for launch before Christmas. The yard was achieving construction times that seemed impossible 6 months earlier. Richmond Yard No. 1 was completing Liberty ships in an average of 67 days, nearly 4 times faster than traditional shipyards. Henry Kaiser's revolutionary approach to ship construction was proving itself through sheer productivity. The prefabrication strategy, the welding instead of riveting, the assembly line organization borrowed from automobile manufacturing, all of it was working exactly as promised. American shipyards were finally building cargo vessels faster than German U-boats could sink them. The mathematics of attrition were shifting in favor of the Allies. Then came Pearl Harbor, December 7th, 1941. The Japanese attack transformed America's industrial mobilization from urgent to desperate. The war that had been Europe's problem, that had driven British orders for cargo ships, suddenly became America's total commitment. Every shipyard in the country received orders to accelerate production beyond what anyone thought possible. At Richmond, Kaiser's response was immediate and dramatic. He announced plans to expand from 1 yard to 3 yards, operating simultaneously on the same site. Employment would triple from 10,000 workers to 30,000 by spring. Construction time would drop from 60 days to 45, then to 30. America needed an ocean of ships, and Kaiser promised to provide them. Welder watched the shipyard transform around him through the winter of 1941 and 42. New workers flooded in daily, pulled from farms and shops across America by newspaper advertisements promising high wages and patriotic service. Women arrived in unprecedented numbers, taking positions as welders, fitters, crane operators, and inspectors. The workforce that had been 98% male in October was 25% female by March. The training program compressed further. 2 weeks became 10 days, then 1 week. New welders went from basic instruction to production line within days, learning only the specific task they'd perform repeatedly. The maritime craftsmen who'd initially supervised production were overwhelmed by masses of workers who knew nothing about ships but could learn to weld a specific seam type after a few days of practice. Quality became a desperate concern, masked by production pressure. Inspectors checked completed welds visually, looking for obvious defects, but they lacked time for thorough examination. The volume of work was overwhelming. Every Liberty ship contained approximately 10,000 individual welds, joining thousands of steel plates and structural members. With ships launching every few days, inspectors faced impossible workloads. Welder kept noticing the warping. It was worse now, with less experienced welders who didn't understand how their work affected the metal. New welders would overheat sections, running continuous beads without allowing cooling time. The steel would twist dramatically, requiring straightening with hydraulic jacks that added even more stress to the structure. He brought it up again with supervisors in February 1942. The welding sequence is creating stress in these sections. I've been testing different approaches on scrap plates. If we weld from the center outward instead of edge inward, the warping decreases significantly. The response was dismissive. "We're building ships in 40 days now. We don't have time to redesign the process based on hunches from a welder with 4 months' experience." The engineering department developed these procedures based on maritime construction principles. Your job is welding seams, not questioning engineers. But the reports from the Atlantic were getting worse. Ships weren't just developing cracks, they were breaking apart. The SS Pontiac, launched from Richmond in November 1941, developed a 30-foot crack in her deck while crossing to England in February 1942. The SS Esso Albany, built at a East Coast yard using similar methods, cracked her keel in calm seas. The SS John P. Gaines, another Richmond-built Liberty ship, fractured completely in half while at anchor in harbour. The Maritime Commission convened emergency investigations in March 1942. Metallurgists examined failed sections. Naval architects reviewed design calculations. Inspectors checked welding quality at shipyards. The conclusions were contradictory and unsatisfying. Some investigators blamed the steel quality. Others identified design flaws in the Liberty ship's squared hull corners. Several reports criticized welding quality and inspector training. Nobody questioned the welding sequence itself. Through spring and summer 1942, Liberty ship production accelerated even as the cracking epidemic worsened. Kaiser's yards were now completing ships in an average of 42 days. Richmond Yard No. 2, newly opened in January, set records with several ships built in less than 30 days. The prefabrication strategy reached extraordinary efficiency as workers gained experience and yard managers optimized every process. The human cost mounted in the Atlantic. Merchant mariners sailed aboard ships they knew were structurally suspect. The cold waters of the North Atlantic, where convoy routes to Britain concentrated, proved particularly deadly. Temperatures below 40 degrees Fahrenheit caused the steel to become brittle. Ships that seemed sound in California's mild climate developed catastrophic cracks when exposed to winter conditions in northern waters. The SS Schenectady provided the most dramatic example. January 16, 1943. The brand-new Liberty ship sat quietly at dock in Portland, Oregon. She'd been built at Kaiser's Oregon Shipbuilding Corporation using identical methods to Richmond's yards. No enemy threatened her, no storm battered her hull. The morning was calm. Then, without warning, a sharp crack echoed across the harbour. Within moments, the entire vessel fractured completely in two, splitting from deck to keel as if sliced by an invisible blade. The ship's back broken while tied safely to the pier. The Schenectady disaster forced a reckoning that previous failures had not. A ship breaking in half while docked removed all ambiguity about enemy action or storm damage. This was purely a structural failure, and it demanded answers that could no longer be deferred or explained away. Joseph Welder read about the Schenectady in the San Francisco Chronicle 3 days later. The newspaper article was brief, noting that investigators suspected welding quality or steel defects, but Welder knew something the investigators apparently didn't. He'd been watching steel warp under welding torches for 16 months. He understood that the stress being locked into these ships wasn't a quality control failure. It was a systematic problem, built into every Liberty ship through the welding sequence itself. He requested a meeting with his yard supervisor, breaking protocol that could result in dismissal. He brought his test plates, samples he'd welded using different sequences, showing dramatic differences in distortion and visible stress patterns. He explained his observations about center-out welding reducing residual stress. The supervisor was skeptical but agreed to elevate the concern to yard management. 2 weeks passed with no response. Welder continued welding bulkhead sections using the standard sequence, watching the steel warp, knowing that somewhere in the cold Atlantic, in ships he'd helped build, carried these locked-in stresses into combat against both enemy submarines and their own structural vulnerabilities. March 1943 brought a breakthrough from an unexpected direction. A metallurgist named Constance Tipper at Cambridge University in England had been studying fracture mechanics in welded ships. Her research identified the phenomenon of brittle fracture in steel at low temperatures. She demonstrated that the sharp corners in Liberty ship hulls acted as stress concentrators, and that welded construction created continuous paths for cracks to propagate. But Tipper's research, while identifying the problem, didn't solve it. The Liberty ship design was fixed. Thousands of vessels had already been built. The steel specifications were established across the industry. Changing either would require years of redesign and retooling that the war effort couldn't afford. The solution, if one existed, had to come from the construction process itself, from the yards where ships were actually being built, from the workers who put torch to steel every day and watched what happened. April 1943. Kaiser himself visited Richmond Yard, No. 1, touring the facilities and meeting with workers as part of a morale campaign. The visits were carefully staged, but Kaiser made himself accessible in ways unusual for industrial magnates. He walked the fabrication shops, stopped at welding stations, asked workers about their experiences. Welder was working a vertical seam when Kaiser's entourage passed through his area. On impulse, he set down his torch and stepped forward. "Mr. Kaiser, I need 2 minutes to show you something about welding stress." The yard manager moved to intercept him, but Kaiser waved him off. "Go ahead." Welder pulled out 2 test plates from his tool bag. "This one I welded edge to center, the way we do production work. This one I welded center to edge. Same steel, same welds, different sequence. Look at the warping." The difference was visible even to untrained eyes. The edge to center plate showed significant bowing. The center to edge plate lay nearly flat. Kaiser examined both plates carefully, then looked at Welder. "You're saying our welding sequence is creating stress problems?" "Yes, sir. Every section we weld carries residual stress from the way we apply the heat. When that steel gets cold, like in the North Atlantic, it becomes brittle. The stress is already there, locked in. A crack starts. It propagates through all that tension we built into the structure." Kaiser turned to the yard manager and chief engineer who'd accompanied him. "Why haven't we investigated this?" The engineer began explaining that welding sequences were based on standard maritime practice, that metallurgists had examined the problem, that multiple factors contributed to the failures. Kaiser cut him off. "Get me test data. I want hull sections built both ways, measured for residual stress, compared under controlled conditions. If this welder is right, we're sending sailors to sea in defective ships because we're too proud to learn from our own workers. That ends now." The tests began within a week. Kaiser's metallurgists at the Richmond laboratory constructed identical hull sections using standard sequences and the center-out method Welder had demonstrated. They used residual stress gauges to measure the locked-in tension. They subjected sections to temperature cycling, simulating North Atlantic conditions. They deliberately initiated cracks to observe propagation behavior. The results were unambiguous and devastating. Standard welding sequences created residual stress concentrations exceeding 30,000 pounds per square inch at key structural points. Center-out sequences distributed stress more evenly, with peak measurements below 12,000 pounds per square inch. When subjected to cold temperatures and crack initiation, the standard sections propagated fractures rapidly. The center-out sections arrested cracks within inches. The steel was identical. The welds were chemically the same. Only the order of operations had changed, yet the structural integrity improved by factors. The engineers initially refused to believe. May 19, 1943. Kaiser called an emergency meeting of his yard managers, chief engineers, and Maritime Commission representatives. The test results were presented along with a proposal that would transform American shipbuilding more profoundly than the switch from riveting to welding had. Every welding procedure across all Kaiser yards would be revised to incorporate stress relief sequencing. Workers would be retrained. Quality inspection protocols would expand to include residual stress monitoring. And most dramatically, Kaiser announced development of an entirely new vessel class, the Victory ship, designed from the keel up to incorporate the lessons written in fractured Liberty ship hulls. The traditionalists objected immediately. Redesigning welding procedures across 7 shipyards employing nearly 200,000 workers would temporarily reduce production. The Victory Ship program would divert resources from Liberty construction that was finally achieving its goals. The Maritime Commission representatives argued that America couldn't afford delays when merchant shipping losses remained critical. Kaiser's response was blunt and recorded in meeting minutes preserved in the National Archives. "We're not delaying anything. We're fixing what's broken. Liberty ships are dying in the Atlantic because we built speed into the construction process, but didn't build in structural integrity. A ship that reaches England is worth infinitely more than a ship that cracks in half halfway across. I'd rather build 95 ships that survive than 100 ships where 5 break apart and kill their crews." The retraining program began across Kaiser's shipyards in June 1943. Every welder, from veterans like Joseph Welder with 18 months of experience to newcomers still in their first week, received instruction in the new sequencing protocols. The training wasn't complex, but it required unlearning habits that had become automatic through thousands of repetitions. The basic principle was elegantly simple. Always begin welding at the geometric center of any section. Work outward in a radial or spiral pattern. Never complete an entire edge before moving to interior welds. Alternate between different areas of the section to prevent heat buildup in any single region. Allow cooling time between passes. Think of the steel as a living material that responds to thermal stress, not as an inert substance that passively accepts whatever treatment the welder applies. For experienced welders, the adjustment was difficult. Muscle memory fought against the new sequences. Men and women who could weld vertical seams in their sleep now had to consciously think about every torch strike, every bead placement. Production speeds dropped temporarily as workers adapted. Ships that had been taking 42 days were taking 48 days by July. The yard managers watched anxiously as construction times increased. Congressional representatives and Maritime Commission officials demanded explanations for the slowdown. Kaiser faced pressure to abandon the retraining and return to proven methods that, whatever their flaws, were producing ships at rates that exceeded all historical precedent. But Kaiser held firm, supported by test data that couldn't be argued with. The ships being built under new welding protocols showed dramatically reduced residual stress. Post-construction inspections revealed fewer cracks and better structural integrity. Most importantly, the Liberty ships launched after June 1943 and exposed to North Atlantic service through the winter of 1943 and 44 showed failure rates that dropped to nearly zero. The SS Benjamin H. Hill, launched in September 1943 from Richmond Yard No. 2, made 6 convoy crossings through winter storms and sub-zero temperatures without developing a single stress crack. The SS William Clark, completed in October using the new sequences, survived a near-miss torpedo explosion that would have fractured earlier Liberty ships. The hull flexed, absorbed the shock, and held together. The ship made port under her own power. By December 1943, construction times had recovered. Welders had internalized the new sequences through repetition, the same way they'd mastered the original methods. Ships were again being completed in 42 days, but now those ships carried structural integrity that earlier vessels had lacked. The temporary production sacrifice had purchased permanent quality improvement. The transformation rippled beyond Kaiser's yards. The Maritime Commission issued revised welding specifications to all 18 American shipyards building Liberty ships in January 1944. The New York Shipbuilding Corporation, one of America's oldest and most prestigious yards, sent engineers to study Richmond's procedures. Their confidential report to the board of directors revealed complete ideological collapse regarding traditional approaches. Kaiser has achieved what our industry considered impossible by refusing to accept our limitations. He treated shipbuilding as a manufacturing problem rather than a craft tradition. He listened to a frontline worker rather than defending engineering assumptions. The result is ships that survive. We must either adopt his approaches or accept irrelevance. The mathematics of Allied victory were being rewritten in ways that extended far beyond construction speed. By mid-1944, American shipyards were launching Liberty ships at a rate that exceeded German U-boat sinking capacity. In May 1944 alone, American yards launched 93 merchant vessels totaling over 1 million tons. German submarines sank 18 Allied ships that same month, approximately 200,000 tons. The Battle of the Atlantic, which had threatened Britain's survival through 1942 and early 1943, was effectively over, not because convoy tactics improved or code-breaking gave advantage, though both mattered, but because American industrial capacity had simply overwhelmed the threat. German submarines couldn't sink ships faster than Kaiser's yards could build them, especially now that those ships no longer sank themselves through structural failure. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Joseph Welder remained at Richmond Yard through the end of the war, eventually training new welders in the stress relief sequencing methods he'd helped develop. His contribution was never publicly acknowledged. No medals, no congressional testimony, no newspaper features. The engineering establishment absorbed his insight and republished it in academic language, as if the discovery had emerged from laboratory research rather than practical observation on a production line. Yet his legacy permeated modern engineering in ways that reached far beyond shipbuilding. Every welded structure built today, from skyscrapers to pipelines to pressure vessels, follows sequencing protocols descended directly from the procedures developed at Richmond Shipyard in 1943. The American Welding Society's Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards. The Trans-Alaska Pipeline, constructed in the 1970s, relied on welding procedures that explicitly referenced Liberty ship methods to prevent cold weather cracking in Arctic conditions. 800 miles of welded steel carrying hot oil through sub-zero temperatures exists because engineers understood the lessons Welder taught. Modern bridge construction inherited the same principles. The catastrophic failure of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, included residual welding stress as a contributing factor. The investigation revealed welds executed without proper sequencing had locked stress concentrations into structural members. Post-disaster code revisions mandated the sequencing and inspection protocols Liberty ship construction had pioneered. The offshore oil industry learned the lesson repeatedly, always at cost. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. Each disaster prompted investigators to examine welding procedures, and each investigation rediscovered principles that Liberty ship construction had proven decades earlier. Nuclear pressure vessels containing reactor cores under extreme temperatures and pressures represent the ultimate application of stress relief welding. The massive steel shells enclosing nuclear reactions cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The engineers designing these procedures in the 1950s explicitly studied Liberty ship construction as their foundational reference. The 5-day construction timeline achieved by Kaiser's yards in late 1942, while impressive as propaganda, was never the real achievement. The Robert E. Peary, built in 4 days and 15 hours, demonstrated what was possible when every variable aligned perfectly. But it was a stunt, a demonstration that inspired workers and impressed officials without representing sustainable production reality. The actual miracle was something far more profound and far less celebrated. It was the willingness to stop, to admit that speed without structural integrity was worthless, to listen to a frontline worker who'd noticed something the engineers had missed. It was the courage to temporarily sacrifice production numbers to redesign processes based on observed reality rather than defended assumptions. That willingness to learn from failure, to incorporate insights from unexpected sources, to prioritize what worked over what theory predicted, that was Henry Kaiser's true revolution. Every modern manufacturing methodology, from Six Sigma to lean production to total quality management, embeds that principle. The worker observing the process often sees what the engineer calculating from a desk cannot. The final statistics of Liberty ship production reveal both the scale of the program and the significance of the mid-war corrections. Between 1941 and 1945, American shipyards built 2,710 Liberty ships. Kaiser's 7 yards alone produced 1,490 vessels, representing 55% of his organization's total output. Of the Liberty ships built before June 1943 using original welding sequences, approximately 12% experienced significant structural cracking. 3 vessels broke completely in half. 19 suffered catastrophic fractures that required emergency repairs or resulted in total loss. Hundreds more developed cracks that, while not immediately fatal, compromised structural integrity and required extensive repair work. Of the Liberty ships built after June 1943 using stress relief welding sequences, the catastrophic failure rate dropped to effectively 0. Minor cracks appeared in approximately 2% of vessels, caught by improved inspection protocols before they propagated. Not a single ship built with the new procedures broke apart spontaneously. The human cost of the early failures remains difficult to calculate precisely. Merchant mariners who died when Liberty ships fractured at sea were often recorded as combat casualties, lost to enemy action or storm damage rather than structural failure. Conservative estimates suggest that between 300 and 500 sailors died directly from catastrophic hull failures between 1942 and 1944. Those deaths purchased knowledge that saved thousands more. The lessons written in fractured steel and cold Atlantic water transformed not just shipbuilding, but the entire approach to welded construction across every industry. Modern engineers designing structures that must withstand extreme conditions, deep-sea oil platforms, Arctic pipelines, pressure vessels, suspension bridges, all of them work with codes and standards that emerge directly from understanding why Liberty ships broke and how to prevent it. Joseph Welder returned to Kansas after the war ended in August 1945. He used his savings from shipyard wages to buy a small farm outside Wichita, raised his children, and lived a quiet life that bore no obvious mark of historical significance. He died in 1973. His obituary in the Wichita Eagle mentioned only that he'd worked in wartime shipyards and later farmed wheat and cattle. But every welded structure standing today carries his legacy in sequenced welds and stress-relieved joints. Silent testimony to the welder who asked why ships were breaking and refused to accept "that's how it's done" as an answer. His observation, elevated through Kaiser's willingness to listen and implemented through systematic retraining of 200,000 workers, fundamentally altered how humanity builds with steel. The Liberty ships themselves are mostly gone now. Of the 2,710 vessels built, fewer than 10 remain. The SS John W. Brown, built in 1942, serves as a museum ship in Baltimore, still operational after more than 8 decades. The SS Jeremiah O'Brien, preserved in San Francisco, actually sailed to Normandy under her own power for the 50th anniversary of D-Day in 1994. These survivors stand as physical reminders of an industrial achievement that seemed impossible when the program began. But the real legacy isn't the ships themselves. It's the transformation of what industries believed possible. The proof that ordinary people, given proper training and opportunity, could achieve extraordinary results. The demonstration that complex products previously requiring years of craft tradition could be manufactured in weeks using systematized processes. The validation that revolutionary improvement required questioning fundamental assumptions rather than defending conventional wisdom. Kaiser's greatest achievement wasn't building ships faster than anyone thought possible. It was creating an industrial culture where a welder with months of experience could challenge engineering orthodoxy and be heard. Where test results mattered more than credentials. Where admitting error and correcting course was valued over defending flawed procedures. Where the question, "Why are we doing it this way?" received serious investigation rather than dismissive platitudes. That culture, more than any specific technical innovation, changed American manufacturing. The workers who learned those lessons at Richmond and Portland and Oregon City carried them into peacetime careers, rebuilding America's post-war economy. The managers who witnessed the power of frontline insights applied those principles across industries. The engineers who saw theory corrected by practice became more humble about assumptions and more willing to learn from observation. Admiral Chester Nimitz, commander of the Pacific Fleet, reflected on the strategic impact of American maritime production in his post-war memoir published in 1960. We fought across 5,000 miles of Pacific Ocean supplied by ships built faster than the enemy could sink them. Japan's military planners assumed American industrial capacity was impressive but finite. They believed that if they sank enough ships, eventually American logistics would collapse. They failed to account for Henry Kaiser and the 200,000 workers who proved that industrial capacity is not fixed, but can be created when necessity demands it. The story of how one welder's observation transformed Liberty ship construction is ultimately a story about listening, about the courage to admit that established procedures might be wrong, about the humility to learn from those closest to the actual work, about the wisdom to value results over credentials, evidence over assumptions, improvement over tradition. Joseph Welder never claimed to have revolutionized shipbuilding. He simply noticed that steel was warping, wondered why, experimented with alternatives, and persisted in sharing what he'd observed, despite dismissive responses from superiors. That simple act of attention, combined with Kaiser's willingness to investigate rather than defend, saved hundreds of lives and transformed an industry. The Liberty ships carried more than cargo across oceans. They carried proof that human ingenuity, when freed from the constraints of conventional wisdom and empowered by necessity, can accomplish what experts claim impossible. They demonstrated that the most important innovations often come from unexpected sources, that the person doing the work sometimes sees what the designer cannot, that progress requires questioning accepted limits rather than defending them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.